Let's look at a set of initial conditions where the temperature of the bar is 1 between L over 3 and 2L over 3 and 0 otherwise. And we want to solve for the unknown coefficients, the b sub n's, and then the temperature of the bar is a function of time. Well, we can do the same thing as we did last example. Set t is equal to 0 in our general solution, and then we set that equal to our initial conditions. Except now we can't just guess the b sub n's, we have to use a Fourier series in order to solve for the b sub n's. If we do the Fourier trick on both sides here, we'll find that the expression for the b sub n's can be written in terms of the initial conditions, u of x comma 0, as 2 over L, the integral from 0 to L, the u at t is equal to 0, times sine of n pi over L x. We need to integrate all of that. So we can just put in our expression that we have for the temperature of the bar at t is equal to 0. And so that means we put in 1 for that temperature, and now the bounds of the integral are L over 3 to 2L over 3, because otherwise the temperature is 0 outside of that region. And we can just do this integral, keeping track of minus signs and factors of L, and then canceling those. We need to evaluate this term cosine of n pi over L times x between L over 3 and 2L over 3. But we can do that, again, taking into account the minus sign, I get this expression for our b sub n's. We can now place this expression for the b sub n's directly into our general solution, and we have now the general solution for the temperature of the bar as a function of time. And it looks something like this. So we have some ugly looking coefficient. We can't seem to do much better than this on this coefficient, times the sine of n pi over L x, and times the corresponding exponential for each n term.